Resonance in real circuits is never perfect or identical across systems. Some circuits produce extremely sharp frequency peaks, while others spread energy across a wide range of frequencies. In this lesson, we will learn the quality factor, or Q factor, and how it controls the sharpness, efficiency, and selectivity of resonance in electrical and RF systems. The quality factor, or Q factor, is a dimensionless quantity that describes how efficiently a resonant system stores energy compared to how much energy it loses in each cycle. It is one of the most important parameters in understanding the behavior of RLC circuits and resonant systems. In simple terms, Q factor tells us how sharp a resonance is. A high Q circuit stores energy very efficiently and loses very little energy per cycle, which results in a very narrow and strong resonance peak. A low Q circuit loses energy quickly, which leads to a weaker and much broader frequency response. This makes Q factor a direct measure of selectivity in frequency domain behavior. It determines how precisely a circuit can distinguish between nearby frequencies and how strongly it responds at its resonant frequency. From a physical point of view, Q factor is based on energy balance inside a resonant system. In an LC or RLC circuit, energy continuously moves between the electric field in the capacitor and the magnetic field in the inductor. This energy exchange is what creates oscillation. However, real circuits contain resistance, which causes energy loss in every cycle. The Q factor represents the ratio of energy stored to energy lost per cycle. If energy loss is small compared to stored energy, the oscillation continues for a long time, resulting in a high Q system. If energy loss is large, oscillations decay quickly, and the system behaves as a low Q circuit. This physical interpretation connects circuit theory directly to real energy behavior in electrical systems. The Q factor directly determines how sharp or wide the resonance peak is in frequency response. A high Q circuit produces a very narrow resonance peak, meaning it responds strongly only around a very specific frequency. A low Q circuit produces a wider resonance curve, meaning it responds to a broader range of frequencies but with reduced peak intensity. This trade-off between sharpness and bandwidth is fundamental in filter and system design. Because of this relationship, Q factor is often used as a design control parameter in engineering. By adjusting resistance, inductance, and capacitance, engineers can shape the frequency response of a system to meet specific performance requirements. In practical engineering systems, Q factor is widely used in the design of filters, oscillators, and resonant circuits. High Q systems are used when precise frequency selection is required, such as in radio receivers, narrowband filters, and frequency selective amplifiers. Low Q systems are used when wider frequency coverage is needed, such as in audio processing, broadband communication, or systems that require stable but less selective response. The choice of Q factor depends entirely on the desired balance between selectivity and bandwidth. However, very high Q systems can become sensitive to small variations in components, temperature changes, and manufacturing tolerances, which may shift the resonant frequency and affect system stability. In RF engineering, Q factor is one of the most critical parameters in resonant system design. It directly affects filter performance, antenna bandwidth, and oscillator stability. High Q resonators are used in applications where frequency, precision, and selectivity are essential, such as communication receivers and narrowband filtering systems. Low Q resonators are used in broadband applications where wide frequency coverage is more important than sharp selectivity. Understanding Q factor allows RF engineers to control bandwidth, reduce interference, and optimize signal clarity in complex communication systems. In this lesson, we learned that the quality factor describes how efficiently a resonant system stores energy and how sharp its frequency response is. It determines the trade-off between selectivity and bandwidth in RLC circuits and plays a central role in both circuit theory and RF system design. In the next lesson, we will conclude Playlist 2 with a complete summary of circuit theory applied to RF engineering.